You know, we are surrounded by fabric pretty much every second of every day, but we almost never stop to think about how it's actually made. Well, today, we're going to pull back that curtain. We're diving into a hidden revolution in the world of textiles, and it goes way beyond just a simple needle and thread. So, if I asked you how fabric is made, you'd probably picture fibers being spun into yarn, and then that yarn getting woven or knitted together, right? It's the classic method. But what if you could just skip the yarn making part entirely? What if you could go straight from a pile of loose fibers to a finished piece of fabric? And that's not just some weird hypothetical question. It's totally real. It's the secret behind a huge and really important group of materials that you touch and use constantly, probably without ever realizing it. The key phrase here is non-woven fabric, and the innovation is honestly a total game changer. By gluing or melting or tangling fibers together directly, we get to completely skip the super time-consuming and expensive step of spinning yarn. This isn't just a small change, it's a massive shortcut in how we make textiles. Okay, so how on earth does that work? Well, the whole idea is actually beautifully simple. It all boils down to a really clever two-step process. Let's get into the how it's made of it all. The very first big step is just creating the foundation. You have to build what's called the fiber web. It's really logical when you break it down. First up is web formation. You're literally just taking your loose fibers and getting them arranged into a flat, even mat. But at this point, it's incredibly fragile. You could just pull it apart. And that's where the second step, web bonding, comes in. This is the crucial part that locks all those fibers together to make a strong, solid fabric. Now, for that first step of making the web, there are a couple of main ways to do it. The dry method pretty much uses air or machines to just spread the fibers out. But the wet method is really cool. It's almost exactly like making paper. You mix the fibers in water to create this kind of slurry, and when you drain the water away, it leaves behind a perfectly formed mat. So once you've got your web, you need to lock it all together. And again, you've got options. You can do it mechanically, using thousands of little needles to literally just tangle the fibers up. You can use heat, that's called thermal bonding, to actually melt the fibers together where they cross. Or you can go the chemical route and just use a kind of adhesive to glue the whole thing together. To really see how elegant this all is, let's just focus on one specific process. It's called spun bonding. This is where the efficiency just gets mind-blowing. It's a method that takes you from raw plastic pellets straight to a finished roll of fabric, all in one continuous, automated process. This diagram basically shows you the magic. You start by melting a polymer and squeezing it through tons of tiny holes. Those little streams cool down and become long, continuous filaments. Then, bam, high-speed jets of air blasts them, which stretches them out and tangles them into a random web. That web lands on a conveyor belt and gets passed through hot rollers that press and melt it all into one solid sheet. It is an entire textile factory crammed into a single machine. So, nonwovens are one incredible way to rethink fabric by ditching yarn. But what happens if we keep the yarn and just rethink how we put it together? Well, that brings us to another technique, one that's ancient but has been totally supercharged for the modern world: braiding. Now, when I say braid, you're probably just thinking of a simple 3-strand plait. But industrially, oh man, it is so much more complex. This tube shape right here is a perfect example. Even though braiding has been around forever, today's tech lets us engineer incredibly sophisticated and seriously strong materials with it. The basic principle is just beautiful. On our braiding machine, you have these carriers with spools of yarn, and they all move in this weaving serpentine path around each other. Seriously, it looks like one of those old-fashioned maple dances. That motion interlocks the yarns at an angle, and that angle creates structures that are naturally strong, flexible, and just fantastic at absorbing energy. So, we've looked at bypassing yarn, and we've looked at interlocking it in new ways. But both of those methods still create basically flat, two-dimensional materials. So, what happens when you need strength in a third dimension? This question gets right to the heart of a huge limitation. Your standard piece of fabric is strong along its length and its width. That's your X and Y axes. But if you try to pull it apart through its thickness, the Z axis, it'll just peel apart in layers. There's just nothing holding it together in that front-to-back direction. And this is the solution. What you're looking at isn't a stack of fabrics glued together. Nope. That is a single, solid block of fabric that has been woven in 3 dimensions. The yarns don't just run left and right and up and down, they also run front to back, locking the entire thing into one solid piece. You have to understand, this is a monumental leap. We've gone from making textiles as 2D sheets to engineering them as 3D structural parts, straight off the machine. Okay, so this is all really cool, but why does it matter? What can you actually do with these crazy materials? Well, the applications run the gamut from the totally mundane to the absolutely mind-blowing. Let's start with the nonwovens. They really are the ultimate invisible workhorses. You use them all the time, but because they're often disposable or hidden away inside of other products, you probably never even give them a second thought. Think about it. The sterile packaging on bandages, the gowns and masks in a hospital, face wipes, the filter in your coffee maker or your furnace, even the stiff material inside a shirt collar to keep it from flopping over. That is the hidden world of nonwovens. Now, let's flip to the complete other end of the spectrum. Those advanced 3D woven and braided fabrics we were just looking at, well, they are quite literally building the future of high-performance engineering. This is where having that third dimension of strength becomes absolutely critical. We're talking about lightweight, super damage-resistant parts for airplanes, medical implants that are designed to replace human tendons and ligaments, parts inside rocket engines that have to withstand unbelievable forces, and of course, a classic high-tech braid, parachute cords. It's pretty amazing when you step back and look at it. Just by challenging the most basic assumption of textiles, that you have to spin a thread first, engineers unlocked whole new families of materials that shape our world, from the operating room all the way to outer space. It really makes you wonder, what's the next fundamental thread from some old technology that's just waiting for us to completely rethink it?